We're still in 12.1 series now. When you see the word series, think sum. So an application might be if you are listing how much money you're making every day in a month, like how much you make on the first day, the second day, the third, that might be a sequence. But if you want to know the total that you made for the entire month, that would be a sum or series. So so series is when you add the terms in a sequence. That's now a series. It has a whole different notation, but once you get used to it, I think you won't mind it. So to notate summation, it's called sigma, sigma or summation. Summation notation for this, sigma or summation notation. So so that we can write it more condensed. So for example, let's just start out with examples. Let's say I want to find the sum of, I'll write it like this. This is the first time you've seen it. It's a cool notation. It goes like this. This is the sigma symbol, sigma, from I equals 1 to 4, for example, of, I'm going to explain what it means in a second, of 2I. So that means, okay, so that's the example. I want to find the sum, and there's this weird looking notation. This means that it's like a counter if you do computer science at all. It means that you can use any letter you want here. This index goes from 1 to 4. Like, so how many terms are there in the sum? There are 4. 1, 2, 3, 4. And each time you plug it in, the value of I, into this expression. So the way you would find the value of this is you would go 2 times 1, so I is 1, plus 2 times when I is 2. It always increases from this value to that value in order, 1, 2, 3, 4. Plus 2 times 3 plus 2 times 4. So we have to add up those numbers to get our total, and that would be 2 plus 4 plus 6 plus 8, which would be 20. So this is the this is called the index. Index goes from 1 to 4. 1 to 4. That's what that means. Let's do another example, and this is the easy direction. Let's do another one. Let's say sigma of k. I'm just going to use a different letter because it's a variable. You can use whatever you want. K goes from 3 to 7 of k squared minus 1. Okay? And I want to evaluate that. All you would do is plug in the numbers 3, 4, 5, 6, 7, going up from 3 to 7 into this expression. So I would start out, okay, the first term would be, so the sum equals, I would do, wherever you see a k, you plug in a 3 to start. 3 squared minus 1 plus 4 squared minus 1 plus dot 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 all the way up to 7 squared minus 1, because you go up to 7. So that would be equal to, it's basically like a perfect square minus 1. So like 8, this is 4 squared 16 minus 1 is 15, plus 5 squared minus 1 is 24, plus 6 squared minus 1 is 36, and the last term right here, 7 squared minus 1 is 48, and I know that's 130. 35. Did I miss that? Yes, very good. Thank you. Nice job, Lily. Okay, let's do, and then there's like fun, simple ones like this. Try this for me. N equals 1 to 6 of 1. What would that be? You know what that would equal? 1 to 6 of just 1. There's no variable to plug it in, so it's just good. The answer is 6. It says the first term is 1, the second term is 1, the third term is 1. 1, 2, 3, 4, 5. You know, the answer would be 6, right? Because there's no, it doesn't change. There's no n in the expression. So you can have fun, simple ones like that. So are there any questions on expanding sigma notation? Okay, now we have to go in the other direction. And that's where we have to think about it a little bit more. So example. So the directions, I mean, this is like what you'd see on a test objective, is write the series in summation notation. In summation notation. Okay, and then we can always check. So let's start with this one. Let's say we have 5 plus 10 plus 15 plus ... plus 100. Okay, and we want to write the in series notation. So right now I can I can already write, like, I know my answer is going to look like that in series notation. So again, we kind of want to relate the terms to the sequence number. So that's the first term, that's the second, that's the third. And what's happening each time? Nice. Times it by 5. Times the sequence number by 5. And then we're going to have to know how many terms. So what is this one times 5? Good. So we know there's a total of how many terms? Okay, so that helps us set up our index. So we'll just use I, since that's the most common. I equals 1 to 20, since it's a finite sum, 1 to 20, of, the pattern is 5 times the index number, 5i. And that would be how you would write your solution. But the cool thing about these is you can't always check, but with these you can. So check by expanding. So now go the other way. Plug in 1, so 5 times 1 plus 5 times 2, ... and then try the last one, 5 times 20, yes. So you should always go back the other way and make adjustments. So we have 3 more examples, because I want to make sure we cover different types here. So let's say we have 1/2 plus 4/5 plus 9/10 plus ... Okay, this is different already, because it's actually goes on and on forever, so it's infinite. So we don't need to know how many terms, but we have to describe the pattern. So what I recommend, we're still trying to relate it to the numbers 1, 2, 3, 4, etc. Is always look at, here's the tip, look at the numerator and denominator separately. Don't try to figure out the relationship between 1/2 and 4/5 and 9/10. Just look at the numerator. What do you notice? 1, 4, 9, 16. Those are perfect squares. So we already know that that's basically 1 squared, 2 squared, 3 squared, 4 squared. Okay, done. Now let's look at the denominator. 2, 5, 10, 17. It's just one more than, yeah, it's just one more than the numerator. Perfect. So whatever the numerator was, you just add 1. So it's like 1 squared plus 1. 2 squared plus 1. Excellent. Etc. So by looking at that, I can go to my answer now. So you have your sigma notation, and you're going to do I equals, and you don't have to start at 1, but you typically do. 1, and you don't have to know how many, it's to infinity. So you put the infinity symbol because it's an infinite series. And you're just going to go, it would just be I squared in the top, and I squared plus 1 on the bottom. And that's your pattern. We're going to do a couple more. So number 3 is 6 plus 36 plus 216 plus 1296. Let's try that. So what, do we see it already? Okay, Sean's very good at pattern finding. He sees it's powers of 6, right? 6 to the 1, 6 to the 2, 6 to the 3, I'm not sure, try it on your calculator. Yes, it works. So 6 to the 1, this is 6 to the 2, this is 6 to the 3, and the last one is 6 to the 4, so the sigma notation, you would say I goes from 1 to 4 of 6 to the I. And we're gonna do one more. Let's try 5 plus 6 plus 7 plus ... plus 12. How can we relate these to the numbers 1, 2, 3, plus what? Okay, so the relationship between each term is that you are adding 1, but we want to relate the number 1 to 5 and 2 to 6. And yeah, yes. You're basically adding 4 every time. Right? So to figure out how many terms, what am I adding 4 to get 12? Good, 8. So there are 8 terms. You want to fill in the pattern for the last one, and that tells you what to put your indices at. So I equals 1 to 8 of 4 plus of I plus 4, or 4 plus I. Now there's this formula. Let's say I want to add, and you'll take advantage of this later in your assignment. There's a story of Gauss, and I'm not an awesome storyteller, but it sort of goes that he figured out in like elementary school or something that the teacher was mad at the class and said, okay, you guys all have to add the numbers 1 to 100, and they didn't have any calculators to use. So they had to go, okay, 1 plus, on paper, 1 plus 2 is 3, plus 3 is 6. Okay, and they had to do for the numbers 1 to 100 without their calculator. Gauss, being very young, at a very young age, figured out a pattern to do it very quickly. So let me tell you what he did using just the numbers 1 through 10, and then you can apply it to anything. So what he did, for example, if I want to add the numbers 1 through 10, is I can go like this. 1 plus 2 plus 3 plus 4 plus 5. Watch this. Plus 6 plus 7 plus 8 plus 9 10. This is the idea of what he did, except he did it with through 100. So what do all these add up to? And how many 11s are there? 5, which is exactly half the number of terms. So really the sum is just 5 times 11, or 55. And so the formula for the sum of n numbers, any n numbers, is the number, half the number of numbers times the number plus 1. It's just this. Like if I want to add the first 10 numbers, I would use 11, right? Because that's, if I double back, yeah, I'll get n plus 1, and then the number of numbers over 2. So if I want to know the sum of the numbers 1 through 100, it's 100 over 2 times 101, or 50 times 101. And then my, all I have to do is 50 times 101, and you'll get it. So you use this to shorten your work, so that you don't have to actually write it out and add those up. Even using your calculator, it's a pain, right? Typing in 1 plus 2 plus 3 plus 4 plus 5. You can just use this formula for the sum of the first n numbers. It's sequential. So this is the formula for the sum of first n consecutive integers.